Yes, I don't know when you want to. Okay. So it's a real honor for me to introduce Professor Tomasz Brzezinski. He has got wonderful results about corings, comodules, Hopf algebras in non-commutative geometry. He has 125 papers in MathSciNet and more than 1,500 citations. And in the past 6, 7 years, he has devoted his research to skew braces, heaps and trusses, getting wonderful results, fundamental results. Professor Brzezinski was born in Poland, and he still has a position also at the University of Białystok, but he got his PhD in Cambridge in 1994, and he has been working at Swansea University in Wales for more than 20 years, maybe even 30. Okay. Well, personally, I have really learned a lot of things from his papers. So it's a real pleasure to have him here at our European Non-Associative Algebra Seminar. And the title of his talk today will be Lie Algebras and Affine Spaces.
Thank you very much, Alberto. Thank you very much for this introduction. You are far too kind to me. But anyway, this talk will be really non-associative in the sense that the usual associativity is replaced by the Jacobi identity or its particular version. I notice among the participants there are some people who attended similar talks that I gave over the past year, because the topic on which I will be talking is was born more or less a year ago, and I got very fascinated about it. Right, so it's a joint work. What I will present is partly a joint work with two of my students, James Papworth in Swansea and Krzysztof Radziszewski in Białystok. And the problem is this. So in the past, well, as Alberto mentioned, a few years, I've been working with heaps and trusses as some algebraic structures, ring-like algebraic structures, which connect rings and braces. And the best viewpoint on them is probably given by in a sort of affine way, where you replace, but there is no addition, but there is a combination of addition and subtraction. And this is a heap. Okay, so the aim of those the algebras or affine spaces, well, brackets on affine spaces or Lie algebras is that usually the algebra is defined on a vector space, but now we would like to have a look at possibility of defining such structure on an affine space. And everybody knows what a Lie algebra is. It's a vector space with a bilinear antisymmetric operation that satisfies Jacobi identity, truly non-associative or Jacobi associative. Now, if you want to bring this definition up to the level of spaces, then the problem arises, or two problems, or majority of the problems arise from the fact that we have neither addition nor zero in an affine space. So in an affine space, every point is, all points are equal. We cannot add points, but we can translate a point by a vector. But if there is no addition, then what does it mean to have something antisymmetric? What does it mean when we change the order? It's a binary operation. The bracket will be a binary operation, but if we interchange the arguments, well, what can we expect to have if we don't have addition, or the opposite to an element with respect to addition? So there's some replacement needs to be made for antisymmetry and Jacobi identity as well. And I will try to explain what they are. Okay, so in the traditional approach, an affine space is a vector space on which, so it's an affine space is a set with a transitive and free action of a vector space. So in other words, traditionally an affine space is defined as a pair. You have a set of points, it's A here, and an underlying vector space. And because we have this transitive and free action, any 2 points in an affine space differ by a unique vector from A to B. So points are A, B, vectors are from A to B. So if you have a point and a vector, then you can, that's the action of the vector space on the affine space, you can translate a point to another point by a vector. So in particular, if we have 3 points in an affine space, then we can consider the operation which looks like this. We take the first point, construct a vector from B to C, and then the shift point A in an affine space through the vector B from B to C to another point in an affine space. So there is an operation like this. Now this operation is defined on 3 points in an affine space. But there is also the underlying linear structure of the vector space. So we can also consider operation like this, that we take 2 points and a scalar, an element of a field. We construct a vector from A to B, rescale it by the scalar lambda, and then we translate point A by this rescaled vector. So it's an operation which combines a scalar and 2 points of an affine space to give an affine space, a point in an affine space. Another classical bit of affine spaces is the homomorphism between affine spaces. So if we have 2 affine spaces, A over the vector space A arrow and B over the vector space B arrow, then an affine transformation is a function between the spaces which induces a linear transformation. And it's a unique linear transformation. It's a condition on F. This is which takes a vector between 2 points A, B, and assigns to it a vector between the values of F on the points A and B. Right, it turns out that in this traditional definition of an affine space, actually the vector space bit is not really necessary for the definition, at least. We can always derive an affine space, a vector space from an affine space. So how to think about it? Well, we should think about an affine space as a set with operations. One is an operation, Turner operation on a set itself, and the other operation is an operation which mixes points in a set, a scalar. So the first this Turner operation turns out to be an abelian heap. Now, what does it mean? A heap is generally it's a set, but in this talk I will assume that the set is non-empty, which is equipped with a Turner operation which satisfies 2 conditions. One is a heap associativity. So if we take 5 elements in our set, then we can apply the Turner operation twice to get 1 single point in the result in the set. But there are 3 different ways of doing this. Two of these ways give the same result. So if I first apply the Turner operation to elements A1, A2, A3, get an element in A, and then apply Turner operation to the result together with A4 and A5, I should get the same result as first applying Turner operation to A3, A4, A5, and then applying Turner operation to A1, A2, and the result of the first application. Okay, so we could call this associativity with shift by 2. So we can shift the brackets inside the bracket by 2 elements, not just by 1, but by 2. And the second condition are the so-called Maltsev identities. So if 2 elements in the bracket are the same, A2 and A2 here are the same, and sit next to each other, then we get is the third element. Now a heap is said to be abelian if we can read the words inside the brackets backwards and forwards, from the left to the right or right to the left, and get the same answer. So ABC is the same as CBA. Now, if we have an abelian heap, then one can derive the property, the sort of third possible associativity distribution of brackets. Namely, if we shift brackets by 1, we also get the same result. This is not true in general, and one can easily derive from the definition that I gave here from A and B, that in general, if you shift a bracket within a bracket by 1, then you have to reorder the elements in the middle. So you would have to change the order of A2, A3, A4 into A4, A3, A2. But since the ordering doesn't matter, CBA is equal to ABC, in the abelian case, we have this middle term as well. So an example which actually exhausts all heaps in a way is the following. If we have a group and a subgroup H, then we can consider the coset corresponding to an element X, and the coset is a heap with this operation. So the operation is take the first element, act with the inverse of the second element, and act with the third element. And because of this inverse here, X in the fourth place meets X in the second place, and they will cancel each other out, and we stay in the same coset. So all cosets of a sub corresponding to a subgroup in a group we have a natural structure of a heap. So this suggests this affine. So heaps are in some sense affine versions of groups. Homomorphism of heaps is a function between the sets which preserves the operation the obvious way. So F applied to the Turner operation is the same as Turner operation applied to the values of F. Okay, so there is a one-to-one in quotation marks correspondence between groups and heaps. Namely that if we have a group, A plus, I write plus for group operation if it's abelian or not. In this case, throughout the talk, later on the operation will be abelian, but in general, this plus does not necessarily mean abelian, commutative operation. So then A is a heap with this operation. So minus B means the inverse of B with respect to the operation plus. I know it looks awkward if it's not commutative, but that's how it is. And on the other hand, if we have a heap, then we can always retract it to a family of groups. So we fix an element in, I call it O in A, and then reduce the Turner operation to a binary operation, again denoted by plus, by evaluating Turner brackets always with O in the middle. This will give a group operation here is the inverse, and O is the neutral element. And if the heap was abelian, the group is abelian as well. Now there's an important observation that if you start with a heap, and so we start with a heap, we convert it into a group, and then choose arbitrarily any element O and convert this group into a heap. Okay, so here we have a group and convert it back into a heap in this form. So I should start again, sorry. So we start with a heap. We make it into, choose any element, make it into a group. Now we have a group, so we can compute the associated heap. And the associated heap will be exactly the heap we started with. Okay, so starting from heap, going to any group which is retracted from this heap, and going back to the heap will deliver the same heap operation, which is very useful because it tells us that we are more used to do binary operations and working with groups rather than with ternary operations. But this tells us that if we want to do any calculations with heaps, with concrete heaps, we can always do calculations, convert them in the group, do the calculations in the group, and come back to the heap. We haven't lost any information that way. Now, I mentioned that affine spaces can be defined in a way which is not dependent on the choice of a vector space. So how does it work? So in a recent paper with Simeon Bras, Bernard Rybołowicz, and Paulo Saraco, we refreshed something which is really known and extended it beyond the actions of rings and fields. But in this talk, F is just a field. What I will give now is genuine definition of an affine space. Okay, so an affine space is a heap with an action of a vector space, which I will denote in that way. So lambda AB goes to lambda acting with the subscript A on B. And this A here I will call a base of the action, which satisfies the following properties. That when we fix a base, then we get a by heap operation. So it means that if I put B here, an element, then I will have a heap operation where the heap structure on F is the structure corresponding to the abelian group. So A minus B, or alpha minus beta plus gamma. And if I fix a scalar here, then I will get a heap operation from heap map, heap homomorphism from A to A. Now, okay, this is maybe not very clear. So what I mean is that we have an associativity of the action. So maybe I'll write it down what I mean, that if we act with lambda A mu AB, that's the same as lambda mu. Lambda mu are scalars acting with the basis A and B. The third axiom is really crucial in the sense that it tells us that this choice of the base actually doesn't matter. So if we define the action with a chosen base, I call A, right? I can always change it, or say the chosen base is C, I can always change it to a base A, any other base. And this is the rule, that lambda acting with A of B is lambda acting on B with the base C, again with the base C on A, and the new base A. We call it the base, the change of base axiom. And finally, if every field has two special elements, the zero of the abelian group and the identity of the multiplicative monoid. So the zero acting the following way, that zero acting on anything will extract the base, and identity acting on every element will extract the element, but does not change the element. So this associative action here is actually by this also unital. Okay, so in the case of a affine space, if you prefer traditional definition, what we have here is just that the heap operation is defined A plus a vector from B to C, and this action, F action, is A translated by the rescaled vector A to B, rescaled by lambda. So this definition of an affine space makes no reference to a vector space. Okay, we have a field and a set and two Turner operations. But where is the vector space? Well, the vector space is hidden, well, there are many vector spaces in fact hidden there, and because we can retract the Turner operation to an abelian group. Okay, so I will write for this A sub 0. So this is a group action obtained from the Turner heap operation. And then if I take this O for the base of my affine action, then actually it's just multiplication by scalars. This satisfies all the axioms of a vector space. So in other words, whenever we retract at a point in a affine space, we'll get a vector space. And sometimes this vector space is called the tangent space to the affine space at O. So that's a possible terminology of this. And with this respect, a vector from A to B is just OAB, the Turner operation OAB. Now, an affine transformation in this vector-free formulation of affine space is a morphism of heaps such that it preserves the affine action of the field. So preservation of the action is similar to what happens in the case of vector spaces. So scalars just jump out, but of course we need to change the base. So F acts on the base because it's already action in B and the element on which we act. Okay, so if we want to think about the A as a vector, as a set over some tangent tangent vector space, then this linear part of the affine transformation is just given here. So evaluate F at A and then make a correction, because with the linear map wants to translate to 0 on 1, 0 vector to a 0 vector. That's a necessary condition. So this little trick here makes sure that F hat of OA, which is the 0 in A, gives OB. And that's the consequence of one of the multi-affine entities. And I should say that I didn't say it's in the case of retracting of heap to a vector space, heap to an abelian group. All those groups are isomorphic to each other, mutually isomorphic, and all the tangent vector spaces to an affine space are isomorphic as vector spaces. Right, so now we have sufficient background to tackle the problem of Lie brackets on affine spaces. And this is a notion which was initially introduced more than 20 years ago now by Katarzyna Grabowska, Janusz Grabowski, and Paweł Urbański. And their motivation was to look at all the geometric structures which arise from an attempt to describe motion of particles without specifying frame of reference. So it's an analytical dynamics or analytical mechanics situation where you have particles moving in a space, and you describe the motion. The traditional way of describing the motion then is you choose a frame of reference. Essentially, you fix your coordinate system, which means you choose a vector space and a basis, if needed, if you want a basis, but at least you choose a vector space. And whatever moves in the Euclidean space, which is an affine space, now it's described from the viewpoint of vectors acting on elements. Now, the person mentioned here, Włodzimierz Tulczyjew, he wanted to get rid of the observer in this description, which makes sense if you think about Galilean principle in mechanics. All points should look the same and be described in the same way. So we shouldn't make choice to describe the motion, and the motion should be independent on the choice in a particular way. But okay, so the Tulczyjew's way of dealing with this is, rather than considering transformations between the frames of reference, he decided to get rid of frame of reference altogether. And this means that we replace description in vector spaces by description of affine spaces. And when you start discussing dynamics, then one of the basic things that appear there are Poisson structures and Poisson brackets. And the Poisson bracket is a Lie bracket as well. So you face the problem of how you formulate Lie algebras and Lie brackets in this situation. Okay, Grabowski, and Turbański, they worked in the traditional approach where a affine space comes equipped with the prescribed vector space. At this point, perhaps I should say that this is not really, from the philosophical point of view, it breaks the principle which underlies Tulczyjew approach, because by choosing the vector space, we choose a frame of reference. But anyway, the definition of a Lie bracket in this situation is, in some sense, easier to deal with. So first of all, how they define a Lie bracket? It's an antisymmetric by affine map. Okay, so every vector space is an affine space in a natural way. So this natural way, maybe I should say it, that if you have a vector space, then this affine action, maybe I should, okay, A and B are now elements of a vector space, is 1 minus alpha B plus lambda A. 1 minus lambda B plus lambda A. Is it right? No. I'm not telling the truth. So I have to wipe it out. It's 1 minus lambda A plus lambda B. Okay, so this bracket, it's a GGU bracket, is defined on an affine space, but it takes values in the underlying vector space. It's a bi-affine transformation, and it's antisymmetric. And because it takes values in something that has a structure, underlying structure of an abelian group, it's clear what antisymmetry means. AB is equal minus BA when evaluated with these brackets. I write V to indicate it's a vector valued bracket. Now, the problem arises when you want to describe the Jacobi identity. Namely, you can't just write this triple operation, because the value of B, C of V is in the vector space, but the bracket takes values, the second entry is from the affine space, not from the underlying vector space. However, every affine transformation has the underlying linear transformation. So you can fix an element A, the first argument, then in the second argument, this thing here will be linear. We have a linear transformation when they're decorated with a hat. So now we can evaluate the second entry by taking an element from a vector space. We can write this equality in the vector space and demand this to be equal to 0. Okay, that's just Jacobi identity, cyclic permutations of, say, ABC. Okay, so the question that they wanted to ask with my PhD student James Papworth was is there a purely intrinsic theory of purely affine intrinsic theory of Lie algebras? Okay, so can we define this sort of brackets and structure without reference to a vector space? And we can. And the definition that we propose is the following. So Lie brackets, I say left because there is a right-handed version of this, but they are left modules, right modules, a similar situation. You can go easily from one side to another. So the theories are equivalent. Okay, so Lie brackets on an affine space A is a bi-affine map with values in A. So it's entirely defined without reference to a vector space, and I'm using the definition of an affine space with no reference to a vector space, which satisfies the following property. The first one replaces antisymmetry. And to see that this is antisymmetry, then I can write the bracket here using the binary operations. So this would read as A plus B minus AA plus BA, okay, is equal BB. So if these two things were 0, then we would have a genuine AB plus BA is equal to 0, whatever the 0 is. And similarly, if you write down this operation, which I should perhaps say that there are 5 terms here. So what I mean by this, you distribute the ternary operations the way you like. So you can put it that way, or brackets in the middle, or on the left. Doesn't matter. It's the same outcome. Okay, so these guys here sit on the plus positions. Those are on the minus positions. And this again looks like, so you have a sum of cyclically permuted double applications of the bracket. Okay, so these conditions are satisfied. Then this space, an affine space with a Lie bracket, is called a Lie algebra. Homomorphism. Okay, so there's another slight modification. If I don't want to think about an action of a field in an affine space situation, but just an unital ring, so such as Z, then we have a term Lie truss for this. But anyway, let's stick to Lie algebras when we have genuine action of a field. And the homomorphism of Lie algebras is a homomorphism of affine spaces, which preserves the brackets in an obvious way. Obvious way meaning f of the bracket AB is f of A, f of B. Okay, so let's look at some examples. So first example is that if you take an affine space and take any scalar, say zeta here, then you can define the bracket in the following way. it's zeta, the fixed scalar, acting with the base A on B. Okay, so if I use vector space notation by fixing some, taking any tangent space, vector space to the space, affine space A, we would have this sort of formula, zeta B plus 1 minus zeta acting with scaling A. So this is a Lie bracket on A. Now, the interesting thing is, I'm not saying this here, but the interesting thing is here that if the affine space has at least 2 points, then the Lie algebras corresponding to this bracket are isomorphic if and only if the chosen scalars are equal to each other. In other words, there are as many non-isomorphic Lie brackets on at least one-dimensional affine space as there are scalars, elements of the field, which somehow is well, which tells us that the theory of Lie brackets is much richer than on affine spaces. It's much richer than the theory of Lie algebras, because if you just start with look at a one-dimensional situation, then on a one-dimensional vector space, you can only decide exactly one Lie bracket, the abelian one, AB is equal to 0 for all elements of the space. In the corresponding affine situation, if it's a real vector space, say, or a real affine space, you would have continuum, non-isomorphic structures. Okay, so a special case in a way of this is, so that's mentions a Lie truss. So we can take as a Lie bracket, we can just take the Turner operation. It's AB, either ABA or BAB. So this you can interpret them as special cases of the above. Okay, so how this is related to the original definition? So there's GGU, Lie algebras. Well, so if A is an affine space over a field F, characteristic not equal to be precisely corresponding to the situation of Grabowski's and Urbański, then for any O in A, there is a bijective correspondence between idempotent Lie brackets, so the Lie brackets as I define them right now, with the bracket that is idempotent. So A bracket with A is equal to A for all A, and those vector valued Lie brackets on A with the underlying vector space AO. And the correspondence is as trivial as you can imagine. So one way the vector valued bracket is defined by ABB0 Turner operation, always the 0 of the affine space, of the vector underlying vector space. And in the other direction is just by shifting. But there is also a theorem which goes in the opposite direction. Okay, so if you have a Lie algebra as defined in this talk, then for any O, we have a vector space, AO, the tangent vector space at O. Then this tangent vector space is a Lie algebra, and this is the bracket. Okay, so we take the bracket on the affine space AB and then subtract the values at AO, at the value at OO, and the value minus, and subtract the value at OB. Now, what is important to note in this theorem, so every Lie algebra would have tangent Lie algebras, which are isomorphic for different choices of O as Lie algebras. Now, what is important to note here is that what I wrote on the right-hand side of this equality is the only way in which you can turn a bi-affine operation, AB, bi-affine operation, into a linear operation in AO. This is the only way. So you are somehow forced to write this right-hand side if you want to get some bilinear operation. And it turns out that this bilinear operation is satisfies both antisymmetric and satisfies the Jacobi identity, which indicates that the definition that I gave is the right definition, because when you reduce to the tangent space, you genuinely get Lie algebra. But perhaps I should mention that in the case of the okay, so you can ask what happens with all those examples. Okay, if you look at this example and look at the tangent Lie algebra, then in every tangent Lie algebra will be the abelian one. AB is equal to 0. So this multitude of affine brackets just reduce to one single Lie bracket. Okay, as everybody knows, an associative algebra can be made into a Lie bracket by taking the commutator. Can this construction be developed for Lie algebras? Well, the answer is again, yes, it can be developed, but we have to define associative multiplications on affine spaces. Okay, and this now leads to the notion of a truss or an algebra, associative algebra. So if we start with an affine space, we can have an associative, demand the existence of an associative by affine multiplication. Okay, so it's a natural thing to develop. And then you can ask what kind of distributivity we get in this way. So there is no addition, there's Turner operation, and there is multiplication, and we have some kind of distributivity. And this distributivity is simply distributivity of the multiplication over the Turner operation. And the system, which consists of an abelian heap and associative operation, which is by affine, is a by heap operation, is known as a truss. So by affine multiplications or algebra is just a linearization of a truss. Okay, so Lie algebras of commutators. So if we have an associative algebra A, so the truss, this is a Lie algebra with the following brackets. And this Turner operation on the left, if you write it in the binary form, then it's AB minus BA. So it's indeed a commutator, but I can't stop here. I need to add some element of A, and this element, suitable element here is just B. Okay, so since this is not, this is a seminar on non-associative structures, so one more non-associative structure is a pre-Lie structure. Okay, so we can, similarly to the pre-Lie algebras, I don't want to go too much into the detail, one can define the affine version of this. So if we have a affine space, we can consider a binary operation on this affine space, which satisfies this left weak associativity, if you like. So we have A dot B dot C. There is this associative distribution, but there are also corrections on the right-hand side. So again, you can think about it. There is a plus here, there's a minus here. and plus there between the terms. And this also will give you a Lie algebra with the bracket as in equation 3. Now, what happens with this commutator, affine commutator bracket? What happens when we look at the tangent vector space? Well, first of all, there is an observation which was made in my paper with Ryszard Andruszkiewicz and Bernard Rybołowicz, is that if you have an associative K algebra, as I should say F, it should be F, and an element, then the underlying vector space is, again, this should be F algebra, and here is the product. Okay, so the product is, we take the original product AB and subtract AO OB at O squared. And again, as was in the case of the Lie brackets, this is the only way in which from the bi-affine operation, so bi-affine operation AB, you can define an affine operation. Sorry, I should say it again. From a bi-affine operation, you can define a bilinear operation. It's the only way. And surprisingly, this produces the associative operation. If operation AB, which is written without anything between elements, is associative, then also the bullet operation is associative. And then if we looked at the tangent Lie algebra, then the induced commutator induced from this affine commutator is just the standard commutator. Okay, I don't know. Perhaps I should. Okay, so I should finish soon. I will just give some concrete example, matrix type of example, so that one can work with and realize how those things work. Okay, so I hope everybody knows that every Lie algebra can be represented in terms of matrices, and the Lie bracket is represented by commutator, and the standard Lie algebras or semi-simple Lie algebras correspond to, or they have a presentation in terms of matrices, matrix Lie algebras. So a similar situation happens in the case of Lie algebras. But of course, sets of matrices are slightly different. So let's look just at one example, which I call special normalized affine matrices. And for the sake of focus, let's look at the complex situation. Okay, I denote by those special normalized affine n by n matrix matrices which are special, so they are traceless, of the size 1 bigger, n plus 1 by n plus 1, and with the normalization property that if you sum up elements in each column and each column and each row, you will always get 1. Okay, so 0 matrix is not one of those, right? Now, this set of matrices has a Lie algebra structure with the operations. And now the operations that I write here on the right of the equalities are the usual matrix operations. So this is a subtraction of matrices, addition of matrices. And it's easy to see that if I subtract 2 matrices, then my normalization property is broken. But if I add back some matrix in which every row and every column sum up to 1, then I get a matrix of the of the required kind. Similar here, this different, well, this affine combination of scalars. This is add up to 1 will give will keep the normalization. Again, here, if I multiply two matrices with this normalization, I will get a matrix of this kind, but then if I subtract, and I will lose the normalization, the normalization will be 0, and then then I add element normalized to 1, with rows and columns normalized to 1, so I'm staying in the set of such matrices. Okay, so some examples, just to see that you can actually describe those algebras quite explicitly. So the dimension 1 example is just one matrix, okay, with the bracket, which is an idempotent bracket. In 2x2 case, or the 3x3 matrices, there are 4 such matrices, or actually, so you have a basis of 4 elements, and the barycentric means that I take a linear combination of those 4 matrices with scalars that always add up to 1. So it's an affine combination of barycentric combination of those 4 matrices. Okay, I can write the brackets. Well, maybe they are not very readable, but I can write this, and clearly the combinations are right, in the sense that the coefficients, the scalar coefficients on the right-hand side always add up to 1. Now, if I set O to be equal to Y, omega to be a third root of unity, and then define EF like this, then we get the standard Chevalier generators of the Lie algebra SL2C. Okay, so the tangent Lie algebra to this Lie algebra is SL2C. And in fact, one can prove more general results, and this is done in my paper with Krzysztof Radziszewski, that if n be such that characteristics of f and characteristic of f minus 1, they do not divide the n, then one can show the following, that there is a Lie algebra isomorphism with the following Lie subalgebras of G ln plus 1. Okay, that's SLNF sitting in the upper left-hand corner. So those are matrices, traceless matrices here, and this element. So in a way, we have a coset. So what follows here is, and here field is a general field with those restrictions on the characteristic. So for all elements O, the tangent Lie algebras are just SLNF. So special linear algebras and n by n matrices with traceless matrices. And one can also show that if those conditions are not satisfied, then there is no isomorphism. Right, and I think that's all that I wanted to say today. So if you have any questions, then please ask. Thank you.
Thank you, Tomasz, for the nice talk. So, are there questions, remarks, suggestions?
I have one question.
Please.
Yeah, Professor Brzezinski, can you move the slide to the definition of Lefebvre's?
Yes.
Yes. So in the antisymmetry condition, so you are
Yes.
taking AB, AA, BA equal to BB. So as
Mhm.
if you are taking bracket with A is like 0. So is
Yes.
it possible to replace AA to BB and BB to A?
Yes. It's exact. So
Can you change it?
yes. So it's you can interchange. So this is equivalent to say, okay, you can put BB here and then AA on the right. Because you can think, so it's good to think about this as to get an intuition that in whatever group structure you choose, it will be like that. Okay, so then you can put those terms on whichever side you want. And as long as you have odd number of terms on each side, then this will this can be written in terms of the Turner operation, and it's an equivalent condition.
Okay. So can you replace AA2 by some other CC, or both you can put BB2 by AA? Will that
Well,
hold?
no, you cannot replace it. So you can't replace this by any CC. It has to be the same A and B only. There is no freedom to replace it by anything which is not A or B.
Why is that?
Okay, so why is that? It's a good question, but because then you see the point here is that this definition does not depend on your choices of A and B. So, but if you introduce a third point, then somehow the relation between the bracket on A and B will depend on this third point. And this violates the affine property that all points in your affine space are play the same role. So inserting you can insert the third element provided that you also explain what are relations between between A and C and B and C.
Okay. Thank you.
Okay, thank you. Are there further questions? Okay, then we thank our speaker again for the nice talk.
Thank you very much.
And see you all in a week.
See you.
Everybody.
Bye-bye.